Intermolecular forces. This is the topic we are going to learn now. What is it? It is the attractive forces that hold particles together in a condensed phase. And we will learn and further what are the different kind of intermolecular forces that exist. So what are the different kinds of intermolecular forces that exist? The first kind of a force you are going to learn is the dispersion force. So these kind of force, where does it exist? Non-polar molecules that like hydrogen, nitrogen, chlorine, they show this kind of dispersion force. Basically, I can say that all the molecules show this kind of force. Dispersion force exists in all of them. The second special kind of force is the hydrogen bonding. Polar molecules that have hydrogen attached to chlorine, oxygen or nitrogen will undergo hydrogen bonding. We even call it as hydrogen bonding is fun to remember it's to which element hydrogen should be attached. Some of the examples are water, ammonia, acetic acid, alcohol and HF. In all these cases, hydrogen is attached to either F, O or N. And the third kind of intermolecular force is the dipole-dipole force, and this exists in polar molecules that does not form hydrogen bonding. For example, PF3, CHCl3. All the molecules will show dispersion force. A dipole-dipole will be there in all polar molecules. Hydrogen bonding is a special case of dipole-dipole interaction in which the hydrogen is attached to either oxygen or nitrogen or fluorine. There is one more kind of intermolecular interaction is there that's called as the ion-dipole interaction. It is a Coulombic attraction between ions in polar molecules. So consider sodium chloride solution. We know that sodium chloride will ionize as sodium ion and Cl minus in a polar solvent. The water is polar. So since the water is polar, the sodium ions get surrounded by the negative end of the oxygen and the chloride ions get surrounded by the positive end of water, that is hydrogen. And this kind of interaction we call as ion dipole interaction, and this generally happens between a soluble ionic compound and a polar solvent. Identify the predominant intermolecular forces in the following. You have to just name the predominant one, and the first one is nitrogen. Nitrogen is a non-polar molecule, therefore the only force that will exist will be a dispersion force. The second compound is xenon. Xenon is an inert gas, again a non-polar one, so for the only intermolecular force will be the dispersion forces. And the third one, water. Water is a polar compound, so it will have hydrogen bonding and dipole-dipole, but hydrogen bonding is the predominant intermolecular force. And then HCl. HCl is a polar molecule, but it cannot form hydrogen bonding, therefore it will show only dipole-dipole interaction. Carbon dioxide. If you write the Lewis structure of carbon dioxide, you see that it is non-polar and it will show only dispersion forces. And ammonia. Ammonia, again we know it's a polar molecule, but it can form hydrogen bonding because hydrogen is attached to nitrogen, hence the predominant is hydrogen bonding. PCl3 is similar to ammonia, but it cannot form hydrogen bonding. It can form only, it will have only dipole-dipole interaction. Ethyl alcohol, C2H5OH, can form hydrogen bonding, and hence the predominant intermolecular force will be hydrogen bonding. And C2H5COOH is an organic acid, and hydrogen is attached to oxygen, and hence it will show hydrogen bonding. All those molecules which are showing hydrogen bonding will have dipole-dipole interaction and also dispersion forces. But since only predominant intermolecular force is asked, all the forces which exist is not given over there. Identify the type of intermolecular forces in the following. So the compounds given are methane, then CH3Cl, methyl chloride, and then methyl alcohol. So they look similar. Let's see whether the intermolecular forces are also similar. Methane is a non-polar molecule, therefore the only force I can see is dispersion forces. Methyl chloride has polar, so it will show dipole-dipole and the dispersion forces. CH3OH, you can see that the hydrogen is attached to the oxygen. So it will have a dipole-dipole interaction. It will, as always, will have a dispersion force, but hydrogen attached to oxygen will give it hydrogen bonding also. You can see that. So all the molecules, though they look same, their forces are different. Let's consider the next set, hydrogen sulfide, then CH3NH2, methylamine, and the last one, CH3OCH3, this is dimethyl ether. Hydrogen sulfide, because it is polar, will show the dipole-dipole interaction. It cannot form hydrogen bonding, but it will have dispersion forces. Then methylamine, hydrogen is attached to nitrogen, so and it is polar, so it will have the two forces, dipole-dipole and dispersion forces, and because hydrogen is attached to nitrogen, it will have hydrogen bonding also. The last one, though it has hydrogen and oxygen, you can see that hydrogen is not attached to oxygen, so it will have only the dipole-dipole and the dispersion force, and this compound cannot form hydrogen bonding. Therefore, it doesn't mean that if a compound has oxygen and hydrogen, it will always show hydrogen bonding. The hydrogen should be attached to the oxygen, then only it can show hydrogen bonding. So we have some more questions to practice. Identify the strongest intermolecular forces in the following. Hydrogen fluoride, it will show hydrogen bonding because hydrogen is attached to fluorine. Potassium nitrate, it's an ionic compound. It will have ion-dipole interactions. Then CF4 is a non-polar compound, so it will have only dispersion forces. And then CHCl3, it's a polar compound, therefore it will have a dipole-dipole interaction, but no hydrogen bonding. Bromine is a non-polar compound, therefore it's only dispersion. And then SO2. SO2, if you draw the Lewis structure, it will have a lone pair, and hence it is polar, so dipole-dipole. C3H7COOH is an organic acid. It will show hydrogen bonding as the predominant one. The last one, FeNO3 thrice, aqueous, that means I have iron nitrate in aqueous solution, therefore it will show the ion-dipole interaction.